So this is my setup using a new electronic component that I've never used before. I wanted to have some way of switching on the rocket electronics without cutting a hole in the airframe tube. Well, let me back up a minute. Here's a nice little round mechanical switch that looks useful to turn on a rocket payload. We can switch it on, we can switch it off. Easy, right? What could go wrong with that? Well, the rocket, when it launches, is going to see about 30 or 40 Gs of acceleration straight up, just from the motor. And there's going to be a lot of vibration and everything as well. So let's turn this switch on and simulate 30 Gs. Oh, look at that. It's off. The switch switched off by itself. Nothing touched it except its own mass. So that's never going to fly. Okay, so that gives us some more requirements for the engineering specifications. No holes in the rocket, and it can't be bumped. And I want to avoid any other inadvertent switch off. And, okay, so what can I use? Can I use a light? Well, this is going to be in daylight, so that's not going to be very good. Radio? Well, radio could have interference, yeah, but the worst problem with the radio was the power consumption. Power is a hard one. I want to use a small battery like this one, this little tiny 400 milliamp hour, and I want to plug it in and assemble a rocket like a week in advance. So a week in advance, using up half the battery, let's say my maximum power consumption is going to be a milliamp. That kind of rules out radio and a lot of other active circuits that you might use. But follow me on this one. So what happens when you close the lid on a laptop? Screen goes off, screen goes on. Just like your refrigerator, right? But how does it know? How does it sit in its laptop bag for weeks or months and be ready to switch on instantly? So there's a magnet somewhere in the screen here, and there's a sensor somewhere down here that's going to sense the proximity of the magnet and turn the screen off when the magnet gets close. Well, it turns out there's thousands of sensors to do this. 3,706, and this is just on one online shop. Some of these sensors have fabulously low power consumption, like a microamp, 1,000th of milliamp. That's something I can use. So after literally days of searching through the 3,706 options, I found the AH1392. So let me zoom in here. This is the AH1392, and it is tiny, really tiny, like grain of dust tiny. This is difficult to pick up with tweezers, and when I dropped one, I lost it in the dust on the floor. Fortunately, it's only 44 cents, so I didn't lose a lot of money in the dust. And this one is the big one of the two. On the data sheet, there's actually one size smaller. And this is the bigger one of the two packages available. So this one's special not only for its small size and low power consumption, but it has two different outputs. It can do different things with a north pole and a south pole. So here's my handy dandy magnet. Red is the north pole. If I face the top of the sensor with the north pole, it'll switch on. South pole switches off. Switch on, switch off. Easy. But, you know, I'm going to need a pretty big hole in the side of the rocket here to reach in with the magnet, aren't I? But the thing with magnets is the magnetic field doesn't come just straight out the poles. It makes a curve around from north to south, or from south to north, depending on your point of view. So just here, next to the magnet, there's north lines coming down here and pointing down. So I can bring that up next to my device, and the north will be pointing down inside the rocket. Flip it over, and the south is now pointing down inside the rocket. Turn on, turn off. So what else is on the circuit board? Well, the biggest, most embarrassing component is the battery connector. This is a small battery plug, but at this scale, it actually looks pretty big. There are smaller ones available. Oh, look, here's one over here. this one has pins that come through the bottom of the board, and on my board I wanted it to be flat, so there's no pins passing through the board. The other thing that I have here is a charge circuit. So I have a USB connector, little LED light, and I'm able to charge the small battery just by plugging it in without having to unplug it and put into another charger. So why the strange shape? Well, I wanted this to fit into smaller rockets too, like this 29mm rocket. In fact, not just fit into the 29mm, but I want it to fit into the coupler here. It's 28mm. And so now I can make in this little red cardboard coupler a payload with a dual deployment that's going to deploy this parachute. So that's going to be done by this guy, the recipient of that sweet battery power. This is an Easy Mini dual deployment altimeter. In this version he's hooked up to a pyro charge, which is on a wire running down the center of the hollow shaft. A little bit of black powder here, and poof, this part of the rocket goes away and deploys a parachute. In the middle here is a passive camera spinner. So this is going to have 1, 2, 3 cameras in it, and the idea is that this fin will allow it to stabilize while the rocket spins around it. This is certainly a bad idea because it really doesn't matter how fast the rockets go in this direction. This fin only feels wind, air going this way. So it's probably going to spin. But I want to do the experiment. I want to see if that is a bad idea or a really terrible idea. And then that one came out of this other one down here, where this is an active spinner. This has a motor in it and a computer and sensors so that this is able to actively stabilize the cameras while it's in flight. And oh, what do we got here? Oh, that's a mechanical switch. Click, click. Yes, well, this is an older design before I came up with a magnetic switch. And I will say in my defense that I didn't cut any holes for this one. This is 3D printed, so all the screw holes are perfectly in line. There's no effort required for this once the initial design is done and tested. So there you have it, from mechanical switch to magnetic switch and back again.